For all the buzz around AI, figuring out if it's truly thinking or just, mimicking brilliantly, that feels like a really fundamental challenge. How do we get past just pattern matching?
It absolutely is. It's probably the core question driving a lot of the really cutting edge AI research right now. How do we build better yardsticks, better ways to measure the, let's say, intellectual horsepower of these systems?
Exactly. And well, that brings us right to this fascinating piece of work we're diving into today. It's a paper called Measuring General Intelligence with Generated Games. And it introduces this completely novel way to benchmark AI called G-Bench.
hmm Yeah, we'll be unpacking this study. We've also got some notes here on sort of the bigger picture of AI timelines and a study guide specifically for the paper itself. Think of this as your fast track to getting your head around a really innovative approach to evaluating advanced AI.
Right. So our mission today is to explore G-Bench and really understand what makes its methodology so different, maybe even groundbreaking. We're especially interested in how it uses AI, to create its own evaluation challenges. Okay, let's unpack this.
So the starting point is this critical challenge with the current landscape of AI benchmarks. There's a real risk, a concern, that the impressive performance we see on standard tests might not reflect genuine intelligence.
You mean because these LLMs are trained on just unbelievable amounts of data?
Precisely. And there's a worry that they might be doing well simply because there's some kind of overlap, maybe hidden overlap, between their training data and the actual benchmark tasks.
Right. It really makes you wonder, are we actually seeing true generalization, the ability to tackle genuinely new problems, or is it more like incredibly sophisticated memorization?
That's the crux of it. And to try and get around this potential pitfall, the researchers behind Bench propose something fundamentally different. Instead of relying on these fixed sets of problems, they're exploring evaluating AI using what they call a data generating process.
A data generating
Yeah,
process.
imagine like an exam that can write totally new, unseen questions on demand whenever you need them. That's kind of the essence of their approach here.
And that's where Gbench comes in. So what exactly is this benchmark, these generated games?
So Gbench is basically a collection of entirely new two-player strategy games. But here's the really innovative twist. These aren't games designed by humans. They are completely generated by language models themselves.
Wait, hold on. The AI is creating the very challenges that are then used to test other AI. Wow, that's a fascinatingly recursive idea. How does that actually work in practice?
That's quite a clever three-stage process, actually. First, they use a powerful language model. OpenAI's O1 model was key for their initial dataset, the one discussed in the paper, to generate natural language descriptions, like just text descriptions of two-player strategy games, designed to be playable in a sort of console environment.
Okay, so the LLM acts like a game designer, writing up the initial concepts and rules. Got it. What's next?
The second step is where it gets technically quite interesting. That same language model then takes those game descriptions it just wrote
Uh-huh.
and automatically implements them as functional environments using OpenAI Gym.
Okay, OpenAI Gym, that's like a standard toolkit for AI environments, right? A sort of sandbox.
Exactly. It's a standard interface. So the LLM is actually writing the Python code. It defines all the crucial bits. The action space, basically, all the possible moves a player can make, the step function, how the game state changes when a move is made, the render function, how you'd visualize the game, and really critically, the logic for figuring out what counts as a valid move at any point.
So the AI isn't just describing the game, it's actually coding it into a playable simulation. That feels like a pretty significant step. And the final stage.
The final stage involves training AI agents, specifically reinforcement learning, or RL agents, to actually play these newly created games. They use a technique called self-play.
Right, where the agent plays against copies of itself.
Exactly, millions and millions of times, guided by an algorithm called proximal policy optimization, or PPO. You can think of it like an AI learning to absolutely master a game just through massive amounts of trial and error against itself.
Okay, so now we've got AI designed games coded by AI and AI agents trained by playing them. How do they then use all this to evaluate the intelligence of other language models? That's the benchmark part, right?
Yes, and this evaluation method is also pretty novel. They take the language models they want to test and have them play directly against these highly trained RL agents. The language model gets the natural language description of the game, just like the one generated in step one.
Okay.
It gets the current state of play, like a snapshot of the game board or a situation, and importantly, a list of only the valid moves it can make right then.
And based only on that text description, the current state, and the valid moves, the LLM has to choose its next action.
That's it. The LLM outputs its chosen move. And its performance, its intelligence in this context, is judged simply by its win rate against that really skilled RL opponent. A higher win rate suggests the language model is better at understanding these brand new rules, strategizing effectively, and just making smart decisions in this completely novel AI-generated context.
Wow. Okay, this whole pipeline sounds incredibly intricate. How do they make sure the games being generated are actually, you know, good games, playable, meaningful, not just gibberish?
Yeah, that's absolutely crucial. They implemented a really rigorous multi-stage filtering process. It's key to ensuring the quality and feasibility of these generated games. First up, they use keyword filtering.
Keyword filtering.
Yeah, to get rid of games that sound like they might be computationally intractable. Imagine a game description that implies like an absurdly huge number of possible actions, something you could never simulate or train an agent on effectively. Like generating entire novels as moves or something. Those get tossed out early.
Okay, that makes perfect sense. Can't train if the game's basically infinite. What's next?
Next is execution filtering. This step is all about making sure the AI-generated game code actually runs without crashing. They automatically test things like, can the game environment even be initialized correctly? Does it give the right kind of info about the game state? Does the visual rendering part work?
Hmm.
They even have really simple, like randomly acting AI agents play against each other, just to catch games that might crash or throw errors during what should be normal gameplay.
Huh. So they're essentially using basic AI bots to debug the games created by the more advanced AI. That's quite a loop.
It is, yeah. They also have timeout filtering. This is to prevent games that could, in theory, just go on forever because maybe the win conditions are badly defined or the move mechanics allow for endless loops. Any game that doesn't finish within a reasonable number of turns or a set time limit is discarded.
Right.
And finally, they filter out games that just show a high rate of unexpected errors or exceptions during all these automated tests, basically cleaning out the unstable ones.
Okay, so that covers making sure the games are functional, they have clear rules, they end. But how do they know if the games are actually strategically interesting? That there's like skill involved, not just pure luck?
Ah, yes, this is a really key step they call establishing an upper bound. They need to confirm these aren't just glorified coin flips, right? They need to know that a skilled player, which in this setup means a well-trained RL agent, can consistently beat a less skilled one.
How do they check that?
Well, they train multiple versions of their RL agents with different amounts of training time, some weaker, some stronger. Then they make these agents play against each other in the generated games. They only keep the games where a more advanced, better trained RL agent achieves a significantly higher win rate. They used a threshold of at least 80% against a less trained one.
Okay.
This gives them evidence that the game actually has strategic depth, that skill matters, and that it's learnable. After going through all of that rigorous filtering from an initial batch of 1,000 generated game ideas, they ended up with 126 distinct, high-quality games for the benchmark.
Wow, 126 out of 1,000. That's a pretty significant cut, but I guess it's necessary to make sure the benchmark is really robust. So what did they actually find when they tested different language models on this G-bench? What were the main results?
The results were really interesting, yeah. They offered some pretty clear insights into the capabilities and limitations of current LLMs. They evaluated a whole range of state-of-the-art models, and they broadly categorized them into two groups. Non-reasoning models think things like GPT-4o, Claude 3.7 Sonnet, LMA 3.370b.
Okay, the big names we often hear about.
Right. And then reasoning models, which included their own models like O1 and O3 Mini, and also DeepSeek R1. These are models perhaps designed with more explicit reasoning capabilities baked in.
And the performance difference between those two groups.
It was pretty stark. The non-reasoning models, the first group, generally got quite low win rates against the trained RL agents, typically only around 7 to 9%.
Only 7 to 9%. Wow.
Yeah. But in stark contrast, the reasoning-focused models did substantially better. Their win rates were up in the range of 31 to 36%. So the headline finding is this really clear separation in performance, seemingly based on that architectural focus on reasoning.
That is a dramatic difference. So what does that tell us about what G-bench is really measuring? It's not just language understanding, clearly.
Exactly. The researchers concluded, and I'm quoting loosely here, that explicit reasoning capabilities are critical for success on G-bench. This strongly suggests that the benchmark is effectively probing a model's ability to do strategic thinking, to plan ahead when faced with totally new rules, and to adapt its approach on the fly. These seem to be skills that the models specifically geared towards reasoning possess to a much greater degree. It really indicates J-Bench is tapping into something quite fundamental about strategic intelligence, maybe in a way standard benchmarks don't quite capture.
That's fascinating. And when the language models did lose, which was most of the time for the non-reasoning ones, was it because they were making illegal moves, like misunderstanding the rules, or were their strategies just bad?
That's a great question, and the failure analysis is quite revealing. The overwhelming majority of the losses weren't because the LLMs were making invalid moves according to the game rules. They mostly understood the rules okay.
Okay.
The losses were primarily due to the RL agent simply winning, outplaying them strategically. This strongly implies that the main difficulty for the LLMs wasn't just understanding the immediate rules of the game, but rather the more complex stuff. Strategic reasoning, planning effectively over multiple turns, anticipating the opponent. They were essentially being outmaneuvered.
Do they give an example of a game where this kind of strategic failure really showed up?
Yes, they highlighted one specific game called Crossover. In this game, the goal is either to get your pieces into the opponent's starting area or to capture all of the opponent's pieces. They saw instances where the language model would make a move that looked okay, maybe even good, in the very short term.
Hmm.
But that move would leave it vulnerable to a clever, longer-term strategic play by the RL agent, ultimately leading to a loss a few turns down the line. It really illustrated this difficulty the LLMs had in evaluating the downstream consequences of their actions, in formulating a robust multi-step strategy.
So it's hitting that deeper, long horizon planning capability. This makes G-Bench feel like more than just another set of tests. What would you say is the core academic contribution here? Why is this potentially a big shift in how we think about benchmarking AI?
I think the central contribution, the really innovative part, is this paradigm shift away from static, predefined benchmark data sets and towards using a data generating process.
Right, because traditional benchmarks are finite.
Exactly, they're finite. And that inherently brings up these twin concerns. One is potential data contamination, the worry that models might have somehow seen or learned from the test data during their massive training runs, even indirectly. And the other is benchmark saturation, the point where models get so good at the finished benchmark that it stops being useful for telling them apart or measuring further progress.
But because G-Bench can just keep creating new games.
Precisely. Its synthetic and dynamic nature means you can, in theory, keep generating entirely new evaluation instances forever. This inherently reduces that risk of data contamination. And maybe even more excitingly, as the AI models themselves get more advanced, the process of generating the games could potentially evolve too, creating harder and harder benchmarks over time.
So the benchmark could scale with AI progress.
That's the idea. They even did a small preliminary experiment on this. They compared the game generation abilities of GPT-4o with their own O1 model. They found that O1 actually produced a greater number of diverse games that passed all their tough quality filters. This hints that future, even more capable LLMs could indeed be used to generate even more sophisticated, more demanding benchmarks down the road.
That sounds like a really crucial feature for keeping our evaluation methods relevant as AI keeps racing forward. Now, you mentioned they also look at the games themselves, the ones that made it through filtering. What did they find out about like their diversity? Were they all kind of similar?
Good question. They investigated the diversity using a code similarity tool called Dolos. They looked at how similar the Python code for different game implementations was. They found a median maximum similarity score of only 0.41.
Okay, 0.41. What does that mean practically?
It's a relatively low score. It suggests that the LMM wasn't just, taking one basic game structure and churning out slightly reskinned versions over and over again. There was some novelty beyond just the boilerplate code you'd expect from using the OpenAI Gym framework.
So, genuine variety in the game mechanics being generated.
It seems so. And to get a better handle on what kinds of games were being created, they used another clever technique. Goal-driven clustering. They basically got another language model to read the game descriptions and sort them into categories based on their core objectives and mechanics.
And what categories emerged?
This analysis revealed 5 broad categories: number games, board games, card games, chance games involving dice or randomness, and combat games.
Interesting mix. Was there any particular category that was more common than others in the final benchmark set?
Yes, interestingly, number games ended up being the most frequent category after all the filtering. They made up nearly 37% of the final set of 126 games.
Huh. Any idea why number games were so prevalent?
The researchers hypothesized it might be because number games based on manipulating numbers according to certain rules are generally easier for a language model to implement correctly and robustly in Python code. So they were just more likely to survive that tough filtering process.
That makes sense. Implementation challenges.
Yeah, and they also noted a significant shift in the distribution from before filtering to after. For example, combat games were generated quite often initially, but their numbers dropped dramatically after filtering. This suggests that defining and implementing balanced, playable combat mechanics might be particularly tricky for current LLMs.
Did they also check if the final code, the Python implementation, actually matched the original natural language description the AI wrote? Was it faithful?
Yes, they did manual inspections on a subset of the games for exactly this, and overall they found a pretty good degree of faithfulness. The code generally did what the description said it should do.
Generally. Were there exceptions?
There were some nuances. They noted some instances, particularly in those common number games, where specific details ended up being hard-coded into the implementation rather than being fully dynamic based on the rules. For example, they mentioned a game called Divide and Conquer, which was about prime factorization.
Okay.
But the actual code had a specific list of prime numbers up to 50 hard-coded into it, rather than, say, calculating primes as needed. The game still worked, it was playable, but it highlights maybe a current limitation in the LLM's ability to perfectly translate every subtle aspect of natural language rules into fully general dynamic code.
That's a really insightful detail. It shows us not just how we can evaluate AI, but also gives us a window into the current capabilities and, yeah, limitations of the AI creating the tests. How does this G-bench work fit into the bigger picture of AI research? Are other people doing similar things?
Absolutely. The paper does a good job of positioning Gbench within that broader landscape. There are definitely other game-based benchmarks out there for evaluating LLMs. You've got things like Jericho, which uses text-based interactive fiction games.
Ah, like Zork.
Sort of, yeah. And GameBench, which uses a curated set of known strategy games. There are others too, like Zero Sum Evil and VGBench. But the key differentiator for GBench, the core innovation they stress, is this fundamental approach of using the language models to generate the games themselves from scratch.
So it's not just playing games, it's the AI being the game designer that's novel here.
Precisely. They also place Big Bench within this larger trend we're seeing towards scalable benchmarking efforts in AI projects like Big Bench, Dynabench, SWeBench for coding, DaBench. These are all trying different ways to tackle those limitations of static, potentially saturated benchmarks we talked about earlier.
Mm-hmm.
And finally, they connect it back to all the important research happening on enhancing reasoning in language models, things like chain of thought prompting, program-aided reasoning where models write code to help them think, using external tools. They argue that Gbench provides a really novel and challenging proving ground to actually test how well these advanced reasoning techniques work when faced with truly unseen problems.
This is an incredibly insightful, a really fascinating deep dive into, yeah, a truly innovative piece of research. So, just to bring it all together, what would you say are the absolute core novel aspects of this G-bench approach?
I'd say there are three main things that stand out. First, its fundamentally synthetic nature. The benchmark isn't a fixed data set. It's this dynamic, continuously evolving data generating process. Second, the unique evaluation method testing LLMs by making them play against specialized AI-trained opponents in these brand new games. And third, its inherent potential for scalability. The idea that the benchmark's difficulty could actually increase over time, driven by the very AI models it's designed to measure.
And thinking about what this tells us right now, what are the main takeaways about current language models based on how they performed here?
I think the research provides pretty compelling evidence, really, that many current state-of-the-art language models, especially those not explicitly designed with deep reasoning capabilities, still struggle significantly. They struggle with the kind of strategic complexity and the demand for genuine generalization that these novel AI-generated games throw at them. It really just underscores how critical developing and integrating robust reasoning abilities is for the next steps in AI for tackling truly new and challenging situations.
So maybe the next big leap in how we evaluate AI isn't just about us humans devising harder and harder tasks, but about, well, empowering AI to create and then solve its own challenges. What does that imply for the future of how we assess AI and maybe even for the ultimate pursuit of general intelligence? It certainly gives you something new, maybe a bit provocative to think about. Thanks for joining me for this deep dive.